Design of solid rectangular slab panel in a floor. The reinforced concrete slab is most important element of supporting vertical loads in the building. Slab transits uh, slab transmits load to supporting walls or beams and sometimes directly to the column by flexure, shear, and torsion. Since slabs have large surface area, they are affected by temperature and shrinkage. Slabs act as deep horizontal girder to resist wind and earthquake forces which act on multi-story frames. Slabs are flexure member and deflection is the criteria which governs the depth of the solid slab. The design of slab can be separately done when supported on rigid supports. In such cases, the analysis of beam and column can be carried out separately. Basic criteria to be satisfied for designing a slab supported on rigid supports. First, the minimum thickness of the slab should be 100 mm. Minimum concrete grade M20. Minimum nominal cover as per table 16 IS 456-2000. Maximum diameter of bar that can be used in slab should be less than D by 8, where D is the overall depth of the slab. 1 meter design strip is taken for the design. Minimum percentage of steel required for HYSD bar is 0.12% and for mild steel it is 0.15% for the total cross sectional area, that is B into D is the overall depth. Maximum allowable spacing for main steel bar in slab should be less than lesser of 3 times the effective depth or 300 mm. Maximum allowable spacing for distribution steel bars in slab should be less than, this is for distribution steel, okay, should be less than the lesser of 5 times the effective depth or 450 mm. Minimum spacing of the tensile bar usually allowed is 75 mm. Slab section should be a singly under reinforced section. Nominal shear stress, that is tau b, should be less than permissible shear stress, that is tau c of concrete, as shear reinforcement are not provided in solid slabs, excluding flat slabs. For solid slabs, shear strength of the concrete is given as tau c into K, where K depends upon the depth of the slab and has to be taken from clause 40.2.1.1 IS 456-2000 page 72. For solid slabs, tau c max to be considered is half of that given in table 20 of IS 456-2000. As deflection is the governing criteria for depth of slab, effective depth is assumed as according to clause 23.2.1 of IS 456-2000. Basic values of span by D ratio for span up to 10 meters. For cantilever it is 7, simply supported 20, continuous it is 26. L by D allowable is equal to L by D basic into KT into KC. KT is obtained from figure 4 and KC is obtained from figure 5 of IS 456-2000. We have to check the slab section for deflection and one-way shear. At least 50% of the positive tensile steel at the midspan will be provided at the support in the considered direction of the span. One-way shear check is done at distance D from the face of the support. Okay. One-way solid rectangular support slab supported on two supports. Okay. It is supported on two supports. Over here, Ly and Lx are of no concern. Actual one-way slab supported on two sides, spanning perpendicular to the supports. This is spanning perpendicular supports. Over here, Lx and Ly does not matter. Okay. We take 1 meter design strip over here. Okay. This is the deflection diagram. Okay. This will deflect like this over here. These are rigid beams or wall. This slab is supported on rigid beam or wall. Okay. So this is the main steel. So 50% of this main steel has to be provided on support. Okay, that is what code says. At least 50%, right? Now this slab is designed for a moment. M is equal to WL square by 8, where L is this. It may be Ly or Lx. Okay. So this is a span. Okay. So that is L. and W is in kilonewton per meter square. Shear force can be found as shown below. This is our slab supported on two supports. Okay, this is one support, this is another support. So this is L by 2. That is L is the L is to be taken as a clear span. Okay, so this is center line. Okay, so this is L by 2. So this is distance D, where we have to take one way shear section at about distance D from the support, right? So we are taking 1 meter strip. The load acting is W, that is kilonewton per meter square. So V is equal to W into this length, that is L by 2 minus D, into 1 meter. So this is how we get V. So nominal shear stress V is equal to no, tau V is equal to V divided by VD. B we found by this formula. B is 1 meter and D is the depth of the section of the slab over here, right? So this is how we find the nominal shear stress. Okay, one way solid rectangular slab supported on four supports. Over here, as the slab is supported on all four sides, the aspect ratio will come in picture. Okay, as this is one way slab, so Ly by Lx will be has to be greater than 2. This is a one way slab supported on all four sides with aspect ratio Ly by Lx greater than 2. Over here, it is must that Lx has to be shorter span and Ly has to be the longer span. Okay, over here Lx and Ly matters. Okay, Ly has to be the longer span, Lx has to be the shorter span. Again, this is the deflection diagram over here. This is the deflection diagram over here. Okay, this deflection is very small and can be neglected, and so we designed this as a one way slab. Okay, we take a 1 meter design strip over here. Okay, anywhere, and design it for a moment m equal to WL x square by 8. Okay, over here we have to take Lx, right? Because the mean span is along Lx. Okay, again check for shear, same fundamentals as we saw above. Okay, so V is equal to W. The WA is the load acting on this 1 meter wide strip into this distance Lx2 by D. Okay, and into 1 meter, that is V, and nominal shear stress tau V is equal to V divided by BD. Okay, okay. Two-way solid rectangular slab simply supported on all four sides. Okay, as it is two-way, the aspect ratio Ly by Lx should be less than or equal to 2. This is slab supported on all four sides with edges not held. Okay, simply supported. So code has given this table. Okay, bending moment coefficients of slab spanning in two direction at right angles simply supported on four sides. Okay, so you can get the coefficients alpha x and alpha y, and you can find mx and my. You can design the main steel mx, main steel ASTX due to mx, and whatever steel main steel you get, okay, you have to provide at least 50% on the support. Similarly, in along longer span, there is ly also. Okay, two-way solid rectangular slab supported on four sides with provision of torsion at corners. Okay, when a two-way slab is having a torsion reinforcement at corner, that is, the corners are held. Okay, the 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 connection between the support and the slab is monolithic. Okay, the corners are not allowed to lift. Okay, so there we have to provide torsion reinforcement. We can see in this figure that torsion reinforcement has to be provided at the corners, and this is top mesh and this is bottom mesh, top mesh and bottom mesh, and the length or the size of the mesh should be 0.21 Lx. Okay, this is Lx, 0.2 Lx, this is Lx, right? So, and the steel to be provided is three-fourth of this ASTX. ASTX is the maximum positive steel along the shorter span, right? So area of reinforcement in each direction of mesh should be 3 by 4 AST X positive. So in direction, this should be three-fourth of this AST X positive. In this direction, it should be three-fourth of AST X positive. Similarly, this is how you get the top mesh, and similarly, you have to give a bottom mesh also. Okay. Table 26, IS 456 2000, page 91, gives the bending moment coefficient for rectangular panel supported on four sides with provision of torsion at corners. This There are nine conditions of slab panels given. Okay. So this is the formula for finding the mx positive, that is positive moment uh, about the shorter span. Okay, Lx, and this positive moment is at the midspan. Okay, and this is my positive, that is moment about the longer span, and that is acting at the midspan over here. Mx negative is the moment at the supports. Okay, moment at the supports, right? uh, about the shorter span. Okay, and my negative is the moment about the supports about the longer span. Okay, so this is how we find mx and my moments, and this is the formula given in the code. Okay, and the nine conditions given in the code are, this is the table 26. Okay, from here, as according to the condition of the boundaries of the slab, we have to select the particular panel, and we have to choose the coefficients alpha x positive, alpha x negative, alpha y positive, alpha y negative. Okay. Now, first, let us see. First condition is interior panel. Number one. This is number one. So this slab is continuous. Uh, is continuous. It is an interior panel. Okay. It has slab on all the four sides. So it is an interior panel. One short edge discontinuous. Two number. Okay, one short edge discontinuous. This is short edge. It is discontinuous, and on other three boundaries are continuous, right? One long edge discontinuous. That is three. So third is this. One long edge discontinuous, right? This is a slab. This is a slab. Okay. Fourth is two adjacent edges discontinuous. This is four. Two adjacent edges discontinuous. Five is two short edges discontinuous. 5. Two short edges discontinuous, two long edges are continuous. Okay, 6 is two long edges discontinuous. 6. Two long edges discontinuous, right? 7. Three edges discontinuous, one long edge continuous. One long edge is continuous, and other three are discontinuous. Three edges discontinuous, one short edge continuous. Okay, so that is this. One short edge is continuous, other edges are discontinuous. And the last one is four edges discontinuous. That is an you can say then it is a slab which does not has all the boundaries are discontinuous. Okay, it's a separate slab, you can say, right? Isolated slab, you can say. Okay, in case of two-way slab, also we also have to do the check for shear. The fundamentals remain the same. Take 1 meter strip, okay, and W into Lx2 by D, Lx2 minus D into 1 meter will give you V, and nominal shear stress is equal to tau V divided by BD. Okay, okay, one-way continuous slab. In one-way continuous slab, we take 1 meter strip, okay, of the slab, continuous slab, and design it as a continuous beam. Okay, so these are the coefficients for bending moment given in the code. Okay, the bending moment coefficients are given in table 12, and the shear force coefficient are given in table 13 of IS 456 2000. Okay, so for using this coefficient, you have to it is must that the criteria given in the code uh, for a continuous beam, okay, should be satisfied. That is, there should be at least three span, okay, and the span should not differ more than 50% of the largest span, and so on, right? So all that conditions that are required to use this coefficient should be satisfied in one-way continuous slab too. Okay. For the design of continuous one-way slab, refer video design of rectangular and T-beam, where the design of a continuous beam has been discussed. This same design procedure has to be followed for designing of continuous one-way slab also. Okay. Now we will start the design of a residential floor. Okay. This is a plan of 2 BHK flat. This is living room, which we name as slab 1. This is kitchen plus dining, which we name as slab S2. This is bedroom 1, slab S3. Bedroom 2, slab S4. Change room, slab S5. And this is passage, slab S6. And this is sunk. Okay. Now, first step is we have to assume the depth of the slab. So here, these are the slab numbers S1, S2, S3, S4, S5, S6, and sunk. This is LX. Okay, dimensions are written over here. Okay, so LX and LY are written. So this is these are LY and these are LX in meters. Okay, and this is the aspect ratio. S1 the aspect ratio is 1.5, S2 1.25, S3 1, S4 1.334, S5 is 2, and S6 is 4. Okay, the aspect ratio is greater than 2, so this is one way slab, and sunk is 1.2. So excluding this, all the other slabs are two-way slab. So we will assume the effective depth D as Lx by 32. So this D is effective depth. Okay. So this turns out to be 125 mm, 125 mm, 125 mm. S4 the effective depth is 100 mm. S5 the effective depth is 90 mm. S6 the effective depth is taken as 75 mm. And for sunk slab the effective depth is taken as 90 mm. Okay, so this is how we assume the effective depth of each slab, right? Okay. Now the weather conditions are mild, and so as per table 16 IS 456 2000, we will consider nominal clear cover as 20 mm. And as per table 5 IS 456, the for mild condition, the minimum concrete grade to be taken is M20. So we will take FCK 20 and nominal cover as clear cover as 20. So we will assume 10 mm dia as per main steel and 8 mm dia to be taken as distribution steel. Effective cover is equal to nominal cover, that is 20 mm, okay, plus diameter, half the diameter of the bar used in design, that is 10 divided by 2, that is 5, this is 25. So effective cover we are going to take is 25. So overall depth will be D plus effective cover. So this will be 125 plus 25, 150, 150, 150, 125, 115, 100, and 115. Okay. Now let us take the loads. Imposed load is 3 kilonewton per meter square. Finished floor load is 0.8 kilonewton per meter square. Dead load due to partition wall we are taking as 1 kilonewton per meter square. Dead load due to waterproofing in sunk we are taking as 2.5 kilonewton per meter square. Okay. So now these are the self weight for four different thickness. This is for 150 mm. This is for 125 mm. This is for 115 mm, and this is for 100 mm. Okay. So we have slab number S1, S2, S3, S4, S5, S6, and sunk. Overall depth. Then live load is 3. Okay. Dead load. Dead load, say for slab S1, is finish load, partition load, and self weight. This is self weight. Okay. So this is how we might find the dead load. In case of sunk slab, this is partition load, this is finish load, this is partition load, this is self weight plus 2.5 kilonewton per meter square is the waterproofing load, right? So this turns out to be 7.175 kilonewton per meter square. So this plus this into load factor 1.5, we get the total load factor. This is how we get the total load factor. So once we get the total load factor, So W we have obtained over here, Lx we know. Now we have to find the coefficients. Okay. Then once we know the coefficient, then we get the moments. So let us find the coefficients. Okay. Right. Now slab S1. So this is slab S1. Okay. This is a slab with one long edge discontinuous. So it falls in condition 3. S2, okay, it is having two adjacent edge discontinuous. So it will fall in case 4, okay. Then S3, okay, over here, one long edge discontinuous. So again 3. S4, this is S4. This is one long edge discontinuous. So again, it falls in 3. S5. So this is S5. Over here, two adjacent edge are discontinuous. This is discontinuous. This is also discontinuous because this slab is sunk. Okay, this slab is at the bottom of the beam. Okay, so the continuity breaks over here. So this comes in condition 4, right? Then S6 is one way slab and sunk slab. Okay, this is sunk slab. So sunk slab, the level of the sunk slab is different than this. This all the slabs are at the top of the beam and this is at the bottom of the beam. Okay, so sunk slab is uh, comes under the condition 9. Okay, that is this continues from all the four sides. Okay, so let us see a section of sunk slab. So this is a sunk slab. This is the level of the floor level, means slab S1, S2, S3, S4, S5, S6, and this is the level for the sunk slab. Okay, so it is not continuous from any side. So it is a slab discontinuous from all the four sides. So we will take the condition as 9. Okay. Okay. So panel type is 9, right? So these are the aspect ratio. Okay, this is Lx. So from the table 26, that is this table. Okay, this using this table, we find the coefficients. Okay, so these are the coefficients from the table. Okay, and once you know the coefficients, this coefficient into this load. Okay, these are slab numbers S1, S2, S3, S4, S5, 6, S5, S6 sunk, and in bracket are the load, that is W acting on that slab. Okay, and on S1 the W acting is 12.825 kilonewton per meter square. On S6 the load acting is 10.95 kilonewton per meter square. Using this formula, W is this is W into Lx square, this is Lx, okay, into coefficients. Okay, so you get the moment mx positive, mx negative, m by positive, m by negative. Okay, now once you get the moment, then we'll start the design. So let us start the design slab wise. Design of slab 1. Overall depth D is equal to 150 mm. In effective depth D is equal to 125 mm. M20 grade is used for concrete, and Fe415 we are using for steel. We will use 10 mm or 8 mm dia as our main strip. Okay. S1 two-way slab. Type of panel is 3. Ly by Lx ratio is 1.5. Lx is 4, and Mx positive Mx positive is 10.5, Mx negative is 13.75, M by positive is 5.75, and M by negative is 7.6. So first step is we will have to find the minimum depth required for the slab. Okay, we know the formula. M is equal to 0.138 FCK BD square in case of FCK 20, right? When the concrete grade is M20. So D is equal to this formula. Take the maximum moment out of this 4, that is 13.75. So we get that depth required as minimum depth required as 70.58. Okay, and we have provided 125 mm, so we are safe and okay. And as we have provided greater depth than required, so the section is under reinforced. Okay, so this formula can be used for rectangular singly under reinforced section for finding EST. So we will be using this formula. ASTX positive is found to be 242.42. Okay, B is equal to 1 meter, D is equal to 125. Okay, FCK is 20, right? And this steel should be greater than EST minimum. Okay, so it is. So that is found to be okay. Spacing, we are going to use 10 dia bar as main steel. The spacing is found to be 323.82 mm. Now, according to code, the maximum allowable spacing for main steel should be lesser of the 3 into D, that is 3 into 125, that is 325, and 300 mm. So lesser is 300 mm. But our spacing is found to be greater than this, so we have to provide 300 mm, which will be uneconomical. So let us try a smaller diameter of bar, and we will take 8 mm dia bar. Okay, the spacing then found is to be 207 mm, which is less than 300 mm. Okay, so we will provide, let us provide 8 mm dia about 200 mm center to center. Okay, so this is the steel which we will provide. We take we round it off this value because we have to take care of accidental errors on site in maintaining the cover and the center to center distance of bar, right? So now let us find EST x negative. You know the moment, okay? Then steel is found to be 321.9 mm square, greater than EST medium. So okay, the spacing required is found to be 156. This should be less than lesser of 3 into D, that is 375 and 300. So this is less than 300. So okay, so let us provide 8 mm dia about 150 mm center to center. Okay, now we will find PT, percentage of steel. Okay, that is found to be 0.268. Now this percentage of steel we will be using for one-way shear check. We will see when we come to that. Okay, now find ESTX negative. Okay, that ESTX negative is found to be 186.06 mm square, greater than EST minimum. So okay, spacing found is to be 270.02. So according to the code, this should be less than 300 mm. Okay, lesser of this two, that is 300 mm. Okay, over here, I would like to add something. Over here, D we are taking is 125, but here you have to take D minus 8, okay? Because this is our slab section, this is our main steel ASTX, and this is the ASTY, okay? ASTY is above the main steel ASTX. So D is for ASTX, that is 125 mm. But for the steel along longer direction, okay, that's ASTY, the effective depth will be D dash, okay. That is D minus diameter of bar. Why diameter of bar? This is 8 mm bar. This is already also 8 mm bar, okay. So this D is up to the center of this bar, and this DD is up from the center of this bar. So 4 mm from this bar and 4 mm from this bar, that is equal to 8. That is equal to the diameter of the bar, okay, which we are using. We are using 8 mm diameter. So I have written over here diameter bar. So over here we have to use D dash, which is equal to D minus diameter bar. So that is why I have taken over here as D minus 8 mm, right? Okay, so please be careful. This is very important. Okay. So the spacing found is 270.02, and over here also this D is D dash, okay, that is 125 minus 8, that is equal to 351, and 300, lesser of these two is 300. This is less than 300, so okay, so let us provide 270 mm center to center spacing of 8 mm diameter, right? ASTY positive is found to be the moment is very less, and the steel is found to be minimum. Okay, so we will be providing 8 mm dia about 275 mm, and this spacing is less than 300 mm, so it is okay, right? So this is how we found the steel for the slab S1. Now we will do the check for one way shear, right? Check for one way shear. Find V using this formula. Okay. So Lx is the clear span. Okay. Clear span, that is center to center is 4 meters minus 0.23 minus 0.23, that is center to center half the beam over here, half the beam over here. So that is point, that turns out to be 0.23. So 4 meters minus 0.23 divided by 2, we get 1.875, right? That is, we get Lx by 2. That's how we get Lx by 2. Lx over here is to be taken as clear span, right? So V is found to be, okay, W is known to us 12.825. This Lx by 2 is known to us into 1 meter wide strip, that is 24.05 kilonewton, right? So this is how we find V. Now we find the nominal shear stress V divided by BD. B is 1000, D is the effective depth of slab at this section, that is 125. Okay. Okay. Now this turns out to be 0.193 Newton per mm square. Okay. B is equal to 1 meter, right? Now we have to find the permissible shear stress. Okay. Now this section D, this section that is for one-way shear, right, is at a distance D from the face of the support, that is face of the beam. Okay. So this section, at this section, the tensile reinforcement is the uh, reinforcement at this support, right? And the reinforcement is at this support is AST x negative, right? This is going to be ASTX negative. So we have to take the percentage of steel of ASTX negative. So percentage of steel of ASTX negative is 0.268. Okay. So we have taken 0.268, right? Now we know, as seen earlier, tau c is equal to K into tau c. K is equal to 1.3, which depends upon the depth of the slab. And this is obtained from clause 40.2.1.1 IS 456 2000. And tau c for corresponding PT 0.268 and M20 grade of concrete, we get 0.38. So this is equal to 0.494 Newton per mm square, which is greater than tau v. So it is safe in shear, right? Now check for deflection. So check for deflection, we do the check for deflection at the mid span along the shorter span, right? So we have to take the tensile steel as ASTX positive, okay? So ASTX positive is found to be 251 mm square per 1 meter. PT is 0.201. So Fs is equal to 0.48 Fi into area of cross section of steel required and provided. So this is provided and required. We found it over here. ASTX required is 242. Okay. So 242.42 divided by 251 is the provided. So that is equal to 232. Okay. So Fs is equal to 232 and PT is equal to 0.201. From graph 4 of IS 456, we get KT is equal to 1.7. Now this is our formula. Lx by D allowable is equal to Lx by D basic into KT into Kc. Kc we are taking as 1 because we are assuming there is no compression steel. Okay. So this is 26, that is for continuous slabs. Okay. KT we get 1.7. So this is equal to 44.2. Now actual Lx by D actual is 4 meters by 125 mm depth, effective depth. This is 32, which is less than 44.2, so it is safe in deflection, right? Now taking similarly slab 2, okay. Overall depth is 150, effective depth is 125, M20 grade Fe415. We will be using 8 mm dia bar, okay. So this is the data, okay. Mx positive, negative, My positive, negative, okay. First find the minimum depth required for the maximum moment, that is maximum moment, that is 68.17 mm. Provided is 125, so less required is less than provided, so the section is singly under reinforced section. We can use this formula for finding AST direct. So ASTX positive is found to be 222 greater than AST minimum, so okay. So providing 8 mm diameters, we get SV as 226, which should be less than lesser of this, that is 375 or 300. 300 mm is lesser than this. So this should be less than 300, which is lesser. So okay. So let us provide 8 mm diameter 220 mm. Okay, instead of 226, we will provide 220, right? This we are rounding off. We could take care of accidental error on site due to maintaining the maintaining the cover on center to center distance of the bar. Right? Similarly, find ASTX negative, which is 299. Okay, greater than AST minimum. So okay, spacing found is 168. Let us provide 8 dia about 160 center to center. Instead of 168, we provide 160 center to center. Right? PT is found to be 0.2512, which will be using for the one-way shear check. Okay. Okay. Now again, ASTX negative. Okay, everything remains the same. This is something which has to be taken care of. Over here, it will be D minus 8 okay, as explained above, right? So it will be 125 minus 8 for this case in y direction, still along y direction, right? So this is 238.6 greater than ASC minimum. So okay, spacing is 210.5. Let us provide 8 dia about 210 center to center, right? ASD Y positive is found to be very nominal, so we will provide 275, which is less than 300 So okay, right? Now, please remember this is the PT which we will take, for which we will find the corresponding tau C. Okay, that is for check for one-way shear, right? Same fundamentals. V is equal to W into Lx by 2 minus G into 1 meter. V is found to be 24.05 kilonewton. Nominal shear stress V divided by Vd is 0.193. Tau C again K into tau C. K is 1.3 as from clause 40.2.1.1, and tau C we get 0.36 for corresponding PT 0.2512 and M20 grade concrete. Okay, so this into this is 0.468, which is greater than this, so it is safe in one-way shear, right? Check for deflection. AST positive. Now check for deflection. Okay, in case of check for shear, we'll take AST tensile ASTS steel at the support. Okay, check for deflection, we'll take, as we are finding that the deflection will be maximum at near the midspan, so we'll take the tensile steel at the midspan along the shorter direction. Right? So that is AST X positive, right? So that is found to be 228.4 and PT is found to be 0.183. Okay. So FS is found to be 234. PT is 0.183. Corresponding KT we get 1.7. And so LX by D allowable is equal to LX by D basic into KT into KC. KC we are taking as 1 because we are assuming that there is no compression still. Okay. KT is 1.7. This ratio is 26. This is 44.2. Actual is 32, which is less than 44.2. So it is safe in deflection. Okay. Now let us come to slab 3. Okay. Same procedure. Okay, overall depth is 150, effective depth 125, M20 grade concrete, Fe4 by steel, and we'll use 8 dia bars. Okay, minimum depth required is 52.48. M is the maximum moment, that is 7.6 over here. Okay, and so this is okay, and under reinforced section, rectangular, so okay, singly under reinforced section, so we can use this formula. AST X positive is found to be 130.3, which is less than AST minimum. Okay, required is 180, so we have to take AST X positive as AST minimum. Okay, so spacing required is 279, which is less than 300. Okay, this is 375, this is 300, lesser of these two is 300. So this is less than 300, so it is okay. So let us provide 8 diabars about 270 center to center. ASTX negative is found to be 173.4, which is again is less than AST minimum. So take ASTX negative as AST minimum, and spacing is found to be 279 again. So let us provide 8 dia bar about 270 center to center, which is less than 300. Okay. Now again coming to this point, there is ASTY negative. Please remember this has to be taken as D minus 8. Okay. Over here it is D. Over here it is D minus 8. Okay. So the effective cover is 125. 125 minus 8 over here. This is 186.06 greater than AST minimum. So okay. Spacing is 270.02. So let us provide 8 dia about 270 center to center. Okay. And AST5 is found to be minimum, which we take as 8 mm dia above 275 mm center to center, which is less than 300. Okay. Now check for one way shear. V is found to be 24.05. Tau is found to be 0.193. Okay. And over here, PT, that is at the support, right, is found to be 0.149. Okay. So we will take the corresponding value of tau C for PT equal to 0.149 and FCK 20. So that is 0.28. K is 1.3 as according to clause 40.2.1.1, and so this is 0.364, which is greater than tau V, so it is safe in shear, right? Check for deflection. So we will have to take EST X positive, right? So that is 186 mm square, PT is 0.149, FS is found to be 233, and for PT 0.149, from figure 4 we get ATS 1.8. So this is equal to 26 into 1.8 into 1, that's 46.8. This actual is 4 meters by D 125 mm, that is 32, less than 46.8. So it is safe in deflection. Now slab 4, okay, D is equal to 125. Effective depth is 100, okay. M20 grade concrete Fe415, and we will be using 8 mm diabars, okay. So find the minimum required depth D for maximum moment 6.8, 6.4, okay. That is 48.15. We have provided 100, okay. D we have provided as 100, so safe, and the section is singly under reinforced section, okay. ASTX is found to be 137.42, less than AST minimum, so provide AST minimum. Take ASTX positive as AST minimum, right? Let us provide 8 mm diabars at 33, which is found to be at 334 mm, okay. But according to code, the maximum allowed spacing should be lesser of 3D, that is 3 into, this is D is 100 over here, okay. This is 100. So this also will be 100, right? Okay, right? So both are 300. So this spacing is greater than 300. So we will provide 8 mm diameter, 290 mm center to center. Okay. We will be taking a little bit lesser than this to take care of the accidental errors, right? Right. Now, uh, coming to the next point, that is ASTX negative, okay. This is found to be 184.3, right, which is greater than AST minimum, okay. Over here you have to take capital D, okay, so it is 125, okay. So this is going to 150 mm, so this is greater than AST minimum, so okay, okay. The spacing found to be is 272.6 mm, so we will provide 8 mm dia about 270 mm center to center, right. Now, this steel is going to be useful in one-way shear. Okay, so PT found to be the ASTX negative, that is steel at the support along the shorter span. Okay, that is 0.186%, right? Now ASTY negative. Okay, over here you have to take D minus 8. Okay, so this is 100, this is minus 8, that is equal to 123.9, which is less than AST minimum, that is 150. So take AST Y negative equal to AST minimum. Okay, the spacing is 334, but the spacing should be lesser of these two. This is 276. This is D minus 8. Okay, this is our D dash actually. 3 into D dash. D dash is D minus 8, the 276 or 300. The lesser of this 2 is 276. So we will provide 8 mm die about 275 mm center to center, right? And similarly, AST Y positive, you also will provide at 8 mm about 275 mm center to center, which is less than 276. Okay. Again, same procedure, right? Find V, that is check for one way shear. This is the section at a distance D from the face of the support. Okay, V is found to be 16.4, tau v is found to be 0.166, and tau c is k into tau c. K is 1.3. Okay, because when the slab thickness is less than 150, the value of k is 1.3. You can refer to clause 40.2.1.1, okay, of IS 456 2000. So tau c is 0.31 for PT, 0.186. So this is zero point 0.4, this is 0.16. Tau is less than tau c, so safe in shear. Similarly, check for deflection. So we will use our tensile steel will be ASTX positive because we are measuring deflection at the center midspan. So over there, the tensile steel will be ASTX positive, right? So that is equal to 173.24. PT is 0.173. FS is found to be 190, and PT is 0.173. So we get corresponding KT as 2 from figure 4 of IS 456 2000. So this is the formula: L by D basic into KT into KC. KC we are taking as 1. KT is 2. L by D is 26 because it is a continuous slab. So this is 52. Actual is 3 meters is the LX. 100 is the D. Okay, so this is 30 less than 52. So safe in deflection, right? Similarly, now coming to design of slab 5, these are the moments. The moments over here are very small, okay? So we will provide the minimum, okay? ASTX positive provide 8 mm dia about 240 mm center to center, okay? Because the minimum, the spacing, maximum spacing should be lesser of 3 into D or 300 mm. So our D is 90 over here, okay? Capital D is 115, effective depth D is 90. So 3 into 90 is 270. So we will provide 240 mm, right? Over here also it is 270. So ASTX negative also we will provide at 8 mm diameter 240. Now ASTY positive, over here D we have to take as 90 minus 8. Okay, this is D dash. So this turns out to be 246. So we will provide 8 mm dia about 240 mm center to center, and this also provide 8 mm dia about 240 mm center to center because the maximum spacing allowed over here is 246, right? Now coming to a design of slab 6, which is a one-way slab, right? Simple. So one-way slab, the design moment is found by WL square x square by 8. Okay. Now Lx is 1. W is 10.95. So this is equal to 1.37 kilonewton meter. For this, we have to find the steel. Okay. So definitely the moment is very small. So we will have to provide the minimum steel. So provide ASD as 8 mm dia about 220 mm because it has to satisfy that maximum spacing should be lesser of 3 into D. D is 75. Okay, capital is 100. D into 3 is there is 225 or 300 mm. Okay, so this is lesser than 300 mm. So our spacing should be lesser than this. So we are taking 220 mm. And in the other direction we have to provide AC distribution. So that we are providing at 8 mm about 290 mm center to center. In case of distribution steel, the maximum spacing should be lesser of 5 times the D or 450 mm. Okay, the 5 times the D is 375. Okay, which is less than 450. So we will provide 8 mm dia about 290 mm. Okay. Now coming to the design of sunk slab. Okay, this is sunk slab. Okay, so these are the moments of sunk slab. Okay, over here the negative moment are 0. Okay, so uh, at support we will provide the 50% steel, at least 50% of the steel of the midspan. Okay, so minimum depth required again for the maximum moment, that is 6.9, is 50.55, provided is 90, which is less than required. So the section is singly under reinforced. We can use this formula. So ASTX positive is found to be 2 to 4, greater than AST minimum. So okay. Spacing is found to be 2 to 4 mm. So let us provide 8 mm dia about 20 mm center to center, right? Now ASTY. Okay, over here again, please remember D is 90 over here. Okay, so over here it will be 90 minus 8. Okay, so ESD X positive is required is 199, 191.7 greater than ESD medium. So provide spacing 262.07. Okay, so let us provide 8 dia about 240 center to center, right? So we have to provide at support 50% of this steel. Okay, 50% of this steel will become 440 Spacing will become 440 But the code says the spacing should not be greater than this or lesser of these two, right? So we'll provide same steel on support too. Okay, so AC negative will provide 8 dia about 220 center to center, and AST Y negative we will provide same as provided over here, right? Dia 8 dia about 240 center to center. Okay, the slab is found to be okay for check for shear and deflection, so it is not shown over here, right? So this is the summary now, right? Slab S1. This is positive steel at mid span Lx, negative steel at support Lx, positive steel at mid span Ly, negative steel at support Ly, right? This is for slab S1, S2, S3, S4, S5, sunk slab, and S6, right? Okay, for S1, this is 8 about 200 center to center, right? Let's see over here. Okay, gray color line shows the positive bottom steel along NX. This is positive steel. This plan shows the bottom reinforcement. This plan shows the top reinforcement. Okay, so this gray line shows the positive bottom steel. Okay, and this green line shows the positive bottom steel along LY. This is along LX. This is along LY. Okay, this red line shows the negative top steel at support along Ly. Okay, and this purple line, that is negative steel at the support along Lx. This is along Lx, right? Now we will see for S1. Okay, S1, the positive steel along Lx is 8 about 200 center to center. So this is S1. This is S1. Okay, so you can see 8 about 200 center to center, right? Now you can see the positive steel along Ly is 8 275 center to center. Okay, so this is 8 about 275 center to center, right? Now this is negative steel 8 about 150 Okay, so this is okay 8 about 150 center to center, right? Now this is the negative steel in on support along Ly 8 about 270 center to center. So this is that steel 8 about 270 center to center, right? This is steel. Now please one thing is to be remembered. Okay, say I take slab S1 and S3. Okay, and I want to provide this negative reinforcement as a support. Okay, then for S1, Alex, over here the steel required is 8 about 150 and for S3 the steel required is 8 at 270 center to center. Then we will provide the least spacing. Okay, so over here, though it is required 8 about 270 center to center, but we will provide 8 150 at about 150 center to center, right? Please remember that. So provide the maximum area on the common edges. Okay, maximum area of the steel on the support uh, on the common edges, right? So this is how which something which you have to take care of. Okay, in case of negative steel, because the moments for the two different slabs at the support will be different. Okay, so provide the maximum steel for the maximum moment. Okay, over the moment for this slab S1 over here is greater than the moment of slab 3 over here, right? So provide this steel for the greater moment. Okay, now this is the standard detailing given in SP 34. For positive steel, you can curtail the bar at 0.15 L. Okay, so This is 0.15 Lx, and over here it is 0.25 L. So it is 0.25 Lx. Okay, Lx of this plan. Oh, sorry, this is Ly, right? Sorry, 0.15 Ly and 0.15 L, 0.25 Ly. So Ly you have to take of this span for this, and for this you have to take Ly for this span. Okay, right? Similarly, over here, this is 0.15 Lx and this is 0.25 Lx, right? So this is how you can curtail you can do the steel detailing as according to this. This is for the bottom steel, right? For top steel, this is to be curtailed at zero point 0.1 L, right? So this is top steel. So this is zero point 0.1 Lx, right? Over here, this is zero point 0.1 Ly, right? Because these are the supports which are not continuous, okay? Which are not continuous. Okay, when the supports are, when slab is continuous, you have to take zero point 0.3 L, zero point 0.3 L, right? So over here you can see 0.3 Ly, 0.3 Ly, 0.3 Lx, 0.3 Lx, right? Okay, so this is how you do the detailing of the reinforcement. Now comes the provision of torsion reinforcement. Okay, so this is very important because as the corners are held in of this two-way slabs, so we will have to provide torsion reinforcement as we saw uh, before. Okay, you have to provide mesh at top and mesh at bottom. Okay, so when the slab is discontinuous on two sides, okay, it's a corner, right? Then you have to provide 3/4 uh, uh, as I explained earlier, that in each direction the steel to be provided is 3/4 of ASTX. This is ASTX. Okay, ASTX is the main positive steel in the shorter direction. Okay, at the midspan. So in this direction, you have to provide 3/4 of ASTX. In this direction, you have to provide 3/4 of ASTX. That will give you a top mesh. And another mesh at the bottom of the slab also you have to provide it with the same steel area, right? Okay. But when we have our slab continues on one side, okay, then over here you have to provide 3 by 8th of the ASTX steel. Okay, this steel should be 3 by 8th of the ASTX, right? This for this is one, this is another, right? This is 0.2 Lx, this is 0.2 Lx, this is 0.2 Lx. This Lx you can keep for the same greater Lx. Say this Lx is 3 meters, this Lx is 4 meters. Then to keep the uniformity, okay, take the greater Lx, right? So zero point 0.2 into this Lx, that's zero point 0.2 into 4 meters will be the size of the mesh, right? So in this direction, provide 3/8 of the ASTX. Take this greater ASTX. This ASTX, and you have one ASTX over here, you have another ASTX over here, but take the greater ASTX of these two so that you can maintain the uniformity. So similarly over here also provide 3/8 ASTX steel area. Similarly in this direction, 3/8 of ASTX. This will be your top mesh. Similarly bottom mesh. Okay, so this is how you provide this torsion reinforcement, right? But when the slab is continuous on all the four sides, then over here you do not require any torsional reinforcement to be provided, right? Okay. Now for uniformity, we will provide 8 mm about 250 mm center to center both ways, top and bottom mesh as torsion reinforcement for the case of ease of detailing as corner reinforcement shown in figure, right? So if you try to give different steel for different corners, then it will become a little bit difficult for the wire binder to uh, place the steel. So for the ease of detailing, you can just give the same spacing and area of steel required at the corners. Okay, so it's up to the designer. He may follow this or he may not follow. But I like to keep things easy, so I prefer to keep the spacing of the bars same, bars of the mesh is same, okay, whether it is over here or over here or over here, okay. So this is how you can provide the torsional reinforcement, right? Now, this is how the load is distributed from slab to beams, okay. To this beam, a triangular load will go. To this beam, a trapezoidal loading will go. If it is a one-way slab, then triangular loading will go. Sorry, rectangular loading will go. Okay, this portion will go to this beam. This portion will go to this beam, right? So these are some formulas. Equivalent UDL WE when the load is triangular. Equivalent equivalent UDL WE when the load is trapezoidal. Equivalent UDL WE when the load is rectangular on the beam. Okay. Okay. So please visit website mmsprogramcivil.com where this all these videos and PDF of this has been uploaded, so you can study at your ease. Okay. This is one important information. Steel chair. Okay, at least minimum of 12 diameter is used for keeping for supporting the top reinforcement. Okay, so this is your bottom reinforcement, this is your top reinforcement. Okay, so to keep the top reinforcement in position, you have to provide a chair like this. Okay, mild steel you can usually torsil is used, okay, to make this chair. Okay, this is the magnified image of this, right? So this keeps the top reinforcement in position, right? So this is very important. Okay. Uh, you can also make computer programs which will make your life very easy. Okay. So the our first slab is 150 mm thick. To D, you have to give overall depth 150 mm, 150. Press enter. Oh, sorry, press tab. Okay. Clear cover we have taken as 20 mm. Press tab. Okay. Fi is 415. Press tab. Fck is 20. Right. Calculate. Okay. So we know in case when the depth is 150 mm, we can not use a diameter of bar greater than d by 8. Okay. So in this slab, we cannot use diameter of bar greater than 16 mm. Okay. The maximum diameter of bar that can be used is 16 mm. You can draw the graphs. This black graph is for 8 mm bar. When you use 8 mm bar, okay, then the graphical representation of moment to the spacing of the bar is shown over here, right? 12 10 mm is red graph, and green graph is for 12 mm, and blue graph is for 16 mm. Okay, so when you we know the design moment. Okay, so say suppose I want to find the spacing for 8 mm steel uh, for the particular moment which I know, then just draw a straight line. In straight line, you will directly get the spacing, right? These graphs are for singly under intersection. Okay, so this is how you can make such programs and can take can find out the most economical solution, and you can come to a decision whether you want to use 8 mm bar or 10 mm bar or 12 mm bar or 16 mm bar, right? So this is how we do the design of a floor slab. Hope you must have found this video useful. Thank you.